Some planets wander the galaxy alone, yet stay warm. Here's the gist in plain words: they trap and make heat. They do it with thick blankets of gas and hot hearts. No sunrise, no seasons, still, energy keeps flowing inside. Picture a midnight world, clouds glowing faintly from within. Its ocean might steam under an endless aurora sky. That is a rogue planet, free of any star. It survives by hoarding heat and wasting none. Let me show how these worlds cheat the dark. You float above a black horizon, stars barely budge. A rogue planet is a world with no star. It drifts through space, unbound by any orbit. That matters because these worlds might outnumber stars. They could ferry oceans, chemistry, and maybe habitats. How do they go free in the first place? Young systems are chaotic, with planets elbowing for space. Giant neighbors sling smaller worlds outward, like cosmic pinballs. Passing stars tug orbits and resonances kick timing off. One hard shove and gravity lets go. The escape is violent, but the planet survives. Its sky turns permanent night, yet its story continues. Surveys hint these nomads are common, perhaps everywhere. Microlensing counts suggest roughly one per star, maybe more. Some studies argue there are several per star, especially small. The range spans between 1 and 5, depending on mass. That is a lot of dark real estate. A galaxy with hundreds of billions might hold trillions. There might be more beaches in darkness than sunlit. Quick mental image: a parade of worlds crossing interstellar lanes. They are quiet to us, yet busy inside. Their engines are heat, pressure, and chemistry. Those engines do not need a sunrise to run. Example in real terms: Jupiter still radiates internal energy today. Earth leaks heat from within, about 40 terawatts, so even a lonely world can keep power flowing. Bottom line, rogue planets are common castaways that keep going. Drop beneath the crust and listen to stone whisper heat. Internal heat is energy stored or made within a planet. You should care because it powers weather, oceans, and life. Where does this heat come from without sunlight at all? First, formation left planets hot from crushing impacts. Rock compressed, iron sank, and friction cooked everything. Second, radioactive elements decay, releasing steady warmth for eons. Uranium, thorium, and potassium tick like tiny furnaces. Third, giants slowly contract, squeezing gas and leaking energy. That gravitational settling is called Kelvin Helmholtz contraction. It runs for billions of years at modest power. Rule of thumb: bigger planets cool slower and live longer. Numbers help fix scale, so let's anchor expectations. Earth releases about 40 to 50 terawatts today. That is roughly 0.08 watts per square meter. A super-Earth could leak several times that surface flux. A young Neptune might glow much brighter, still shrinking. Jupiter radiates more heat than it absorbs from sunlight. Remove the sun and it would still shine in infrared. Newly ejected giants stay warm for hundreds of millions. Even after gigayears, the interior remains toasty. Example case: a 10 Earth mass planet after 2 gigayears. It could deliver 0.1 watts per square meter. With a dense blanket above, that is room temperature. So the picture is simple: inner fires never quit entirely. Stand on a windless plain under a black canopy. The air is thick, tasting faintly metallic and cold. A thick hydrogen atmosphere acts like a thermal blanket. It matters because it recycles scarce heat instead of losing it. Here is how that blanket traps warmth efficiently and quietly. Hydrogen is light, so it convects easily when warmed. Rising parcels carry heat upward, then radiate slowly to space. Pressure grows with depth, which raises temperatures through compression. That is the adiabatic lapse working like a heater. Mixed with methane and ammonia, it blocks infrared escape. Clouds form layers, bouncing radiation around like mirrored halls. The net result is less cooling and stable temperatures. Example in real terms: a few tens of bars. Combine that with 0.1 watts per square meter. Surface temperatures can hover near liquid water conditions. Stevenson proposed this decades ago, and models keep agreeing. Even a feeble internal flux becomes habitable with hydrogen. One sentence recap: warm blanket plus small furnace equals comfort. For clarity, this is not fantasy. Young giants already prove it. Brown dwarfs and gas giants glow from within, visibly. Their spectra show the same physics, scaled to darker worlds. What to remember: hydrogen is the quiet hero here. Crack the ice and a black ocean breathes below. An ice-covered world can hide a liquid sea beneath. That matters because ice is an excellent lid for heat. The process is straightforward and elegant at planet scale. Rock and water trap radiogenic warmth in the mantle. The base of the ice warms and begins melting. Convection churns the ocean, distributing energy and nutrients. The shell thickens until heat loss balances inner supply. Fractures open, refreeze, and pump chemistry through the ocean. Salts and antifreeze molecules lower melting points, extending the habitat. Example case, a super Earth with 50 kilometers of ice. Internal heating of 0.05 watts per square meter. That supports a global ocean hundreds of kilometers deep. No sunlight reaches it, yet hydrothermal vents blaze. On Earth, such vents power dense ecosystems without photosynthesis. The same trick could run on a rogue ocean. Tiny test, cover a pot and lower the flame. The water still simmers because the lid conserves heat. Planets use the same kitchen physics, just grander and colder. Bottom line, thick ice turns darkness into a stable incubator. Green curtains ripple over the night as particles rain down. A magnetic field is a shield made by a molten core. You care because it deflects charged particles that erode atmospheres. Here is how the dynamo works inside a planet. Conductive fluid moves and rotation twists those flows. Electric currents build, which sustain a global magnetic field. Hot interiors help by keeping the core liquid longer. Faster spin also helps by stirring the conductor harder. Without a star, the solar wind is mostly absent. Cosmic rays still arrive, fast and penetrating from space. A strong field and thick air blunt much of it. Example numbers: Earth's field is about 50 microteslas. Jupiter's field is 10 times stronger at its cloud top. A super Earth could sit somewhere between those values. Combined with a 100-bar atmosphere, shielding is substantial. This reduces atmospheric loss and surface radiation doses. One-sentence recap: a working dynamo buys time for life. Quick mental image: auroras dancing over an eternal polar night. The sky glows green while the ground stays safe. Net result: magnetism and mass guard the precious blanket. Silence breaks as a comet slams into the dark plane. Impacts are sudden heat injections, delivered from interstellar space. That matters because each strike stirs chemistry and melts ice. Mechanically, the energy converts to shock, fractures, and heat. Hot plumes rise, lakes form, and gases mix vigorously. Some molecules synthesize in the fireball, then rain out. After the flash, the crust seals, trapping warmth for years. Meanwhile, giants tap a slower engine, gravitational contraction. Gas settles inward and pressure turns into heat. The planet radiates that energy away very slowly. The cooling curve is shallow for massive envelopes. Example numbers: a Jupiter mass world emits quadrillions of watts. Think about 10 to the power of 17 watts. A series of large impacts might add comparable spikes. They are rare events but memorable for the planet. Smaller bodies get less from contraction but still gain. Their winds come from decay heat and impact seasoning. Rule of thumb: big planets glow, small planets simmer. Both can hit temporary warm spells after big collisions. Bottom line: chaos above keeps the hearth alive below. Now try finding one against a black, starry background. We detect rogue planets mostly through gravitational microlensing. That means a passing planet briefly magnifies a distant star. It matters because it reveals mass without seeing the planet. Here is how the flash unfolds across the sky. The planet's gravity bends light, forming a temporary brightening arc. As alignment peaks, brightness rises, then falls back to normal. Short events mean low mass, while longer ones mean heavier. Durations range from hours to days, depending on speed. Ogle and MOAA surveys have caught such flashes for years. A famous ultra-short event suggested an Earth mass nomad. Estimates from these surveys feed the counts we cited. Infrared telescopes also hunt the youngest, still warm giants. They glow faintly, especially in the mid-infrared bands. The Roman Space Telescope will push microlensing much deeper. Euclid and ground arrays add cadence and sky coverage. One-sentence recap: gravity outs these worlds even when light fails. Example in real terms: a one-day lens suggests a few Earths. A 10-day curve hints at a Saturn mass loner. With better cadence, we will weigh darker, colder drifters. Steam rises from a black ocean lit by blue sparks. Life without sunlight means chemistry eating rock, not light. That matters because energy budgets decide if ecosystems persist. The playbook copies Earth's deep sea vents, adapted for global darkness. Water meets hot rock, and minerals swap electrons efficiently. Hydrogen, methane, and sulfides feed microbes, which feed others. Circulation carries nutrients across basins, even under thick ice. Occasional impacts dump metals and stir the pot. How much power could such a biosphere capture, realistically speaking? Earth's vents host dense life on a few milliwatts each meter. A rogue ocean with similar flux could support patchy communities. Scale a planet-wide sea, and totals become impressive. Trillions of watts might circulate through chemistry, steadily and quietly. Example scenario, a 15 Earth mass water world with vents, internal heat at 0.1 watts per square meter. That yields enough energy to run microbial food webs. Add dissolved gases from the mantle, and complexity climbs. One sentence recap: no sun required, chemistry pays the bills. The wild part is distance, not physics or biochemistry. Net result, life could ride in darkness for geologic ages. So yes, a planet can wander forever, yet stay warm. The trick is simple: thick blankets and stubborn inner fires. Hydrogen can hide oceans, and ice can save them. Magnetism helps keep the air, while gravity feeds heat. Impacts spice the chemistry and stir the surface. Gravity itself keeps giants glowing for ages, quietly but persistently. That was the secret behind the first line we spoke. If this reshaped your picture of space, stick around. I have more strange worlds to share very soon. Thanks for watching, and feel free to join me again.